Hello, everybody. Glad to see you again. And let's start our lecture. Okay. So let's in today we have lecture number 14. The topic of our lecture is sensor systems in engineering. Sensors like semiconductor strain gauges, tachometers, RTD, temperature sensors, cameras, piezoelectric accelerometers are needed to measure, or as we can say, sense unknown signals and parameters of an engineering system and its environment. Essentially, sensors are needed to monitor and learn about the system and possible interactions with its surroundings. This knowledge will be useful not only in operating or controlling the system, but also for many other purposes, such as process monitoring, experimental modeling, and model identification too, product testing and qualification, product quality assessment, fault prediction, detection, and diagnosis, advisory and warning generation, and surveillance. A common application of sensor is in automobile, where a vast variety of sensors are used in the powertrain, driving assistance, safety, and comfort, and so on, as presented in this slide. Some examples of commercially available sensors are given here. And first of all, as a motion sensor, potentiometer, differential transformer, magnetoresistive or temposonic displacement sensor, magnetic induction proximity sensor, tachometer, resolver, synchro, gyro, piezoelectric accelerometer, laser ranger, and ultrasound range. Here and another class of sensor, force or torque sensor, as this represents the semiconductor, strain gauge, and motor current sensor. Next class is a fluid flow sensor. It represents as a Coriolis flow meter, Pitot tube, rotameter, and orifice flow meter. Next class, pressure sensor. It represents as manometer, Bourdon tube, and diaphragm type. Temperature class sensors as thermocouple, thermistor, and resistive temperature detector, RTD. Let's start with a sensor system. A sensor system may mean, first of all, as a system of multiple sensors, including sensor network and sensor data fusion, when one sensor may not be adequate for the particular application. And second, a sensor and accessoire that will be necessary in implementing it in a practical application, like signal processing, data acquisition, data transmission, and communication. Several examples of sensor systems in both of these categories will be introduced in this lecture and further studied in subsequent our lectures. Our lecture concerns both individual sensors and sensor systems. It will be present the physics and the principles of operation, ratings, and performance specification, selection, necessary hardware and software for integration into the engineering system, signal processing and data analysis, parameter estimation and decision making, and certainly practical application relating to sensors and sensor systems used in a control system. Sensors and sensor systems are indispensable in a control system. A control system is a dynamic system that contains a controller as an integral part. The purpose of the controller is to generate control signal, which will drive the process or plant that is being controlled in desired manner, like according to some performance specifications and using various control devices. Specifically, in a feedback control system, the control signals are generated based on the sense response signal of the plant. Sensors and other main components in a feedback control system are schematically shown in this figure. The measurement from a sensor may not provide the true value of the required parameters or variable for two main reasons. First of all, its required quantity is not directly measured and has to be computed from the measured value using a suitable method. And second, the sensor or even the sensing process is not perfect and will introduce measurement error. And hence, sensing may be viewed as a problem of estimation where the true value of the measurement quantity is estimated using the measured data. Two main categories of error, model error and measurement error, enter into the process of estimation and will affect the accuracy of the result. The model error arises from the relationship between quantity of interest and the quantity that is measured or the model of the system. Unknown and random input disturbances may be also treated under model error. The measurement error will arise from the sensor and the sensing process, like how the sensor is mounted and how the data are collected, communicated, and reported. It is clear that estimation of parameters and signals is an important step of sensing, right? Many methods are available for estimation, and some of them will be presented in our module, like least squares, maximum likelihood, Kalman filter, extended Kalman filter, and unscented Kalman filter. Apart from the conventional sensors, many types of innovative and advanced sensors are being developed. Several types are listed as follows. And first, micro-miniature and embedded sensors, those based on integrated circuit technologies and micro-electromechanical systems technologies with integrated signal processing, control, and other hardware. Sensors may be integral with the system component. Second, intelligent sensors, built-in information preprocessing, reasoning, and inferencing to provide high-level knowledge-based decision-making. Multi-sensor fusion to provide more reliable and accurate results. Third, network sensors or multiple sensor nodes communicate with each other in a distributed sensing setup. There can be significant geographic separation between S and S. The node connection may be wired or the wireless. Typically, an SN contains on one or more sensors, a microcontroller and signal conditioning hardware. And four, hierarchical sensory architecture. This may be represented as a low-level sensory information is preprocessed to meet high-level requirements. For example, in hierarchical control, Each control layer is serviced by a corresponding sensing layer. Sensors and transducers in our application scenarios are necessary to acquire output signals or process response for system monitoring, fault prediction, detection, and diagnosis. And certainly, generation of warning and advisors. It may be used for feedback control and supervisory control, and to measure input signals for experimental modeling or system identification, and certainly for feed-forward control and for a variety of other purposes. Sensors and transducers are necessary to acquire output signals, as we already did. So, since many different types and levels of signal are present in a dynamic system, signal modification, including signal conditioning and signal conversion, is indeed a crucial function associated with sensing. In particular, signal modification is an important consideration in component interface. It is clear that the subject of system instrumentation should deal with sensor, transducers, signal modification, and component interconnection. In particular, the subject should address the identification of the necessary system components with respect to type, function, operation, and interaction, and proper selection and interfacing of these components for various applications. Parameter selection, including component sizing and system tuning, is an important step as well. Design is a necessary part of a system instrumentation. For it, its design that enables us to build a system that meets the performance requirements. Starting perhaps with a few basic components such as sensors, actuators, controllers, compensators, and signal modification devices. Engineers, particularly mechatronic engineers, should be able to identify or select components, particularly sensors, actuators, controllers, and interface hardware for a system, to model and analyze individual components and the overall integrated system, and to choose proper parameter values for the component, like component sizing and system tuning for the system to perform the intended function in accordance with some specification. Instrumentation includes sensors, actuators, signal acquisition and modification, controllers, and accessories, and their integration into a process is applicable in branches of engineering. Typically, instrumentation is applicable in process monitoring, fault prediction, detection, and diagnosis, testing, and control in practically every engineering system. Some branches of engineering and typical application situations we may list it as follows: aeronautical and aerospace engineering for aircraft and spacecraft, civil engineering for monitoring of civil engineering structures like bridges, buildings, etc., chemical engineering for monitoring and control of chemical processes and plants, electrical and computer engineering for development of electronic and computer integrated devices, card drivers, sensors embedded systems, and control and monitoring of electrical and computer systems. Material engineering for material synthesis processes and material tests. Mechanical engineering for vehicles and transit systems, robots, manufacturing plants, industrial plants, power generation systems, jet engines, oils and gas extraction, transportation and refining. Mining and mineral engineering for mining machinery and process and raw material, nuclear engineering for monitoring and control of nuclear reactors, and testing and qualification of components. We have highlighted the automotive examples as a valuable application scenario for sensors and sensor systems. Several applications and their use of sensors are noted in this table. Some important areas of application are indicated here. As noted before, transportation is a broad area where sensors have numerous applications. In ground transportation, in particular automobiles, trains, and automated transit systems, use airbag deployment systems, anti-lock braking systems, cruise control systems, active suspension systems, and various devices for monitoring, toll collection, navigation, warning, and control in intelligent vehicular highway systems. All these devices use sensors and sensor systems. In air transportation, modern aircraft designs with advanced materials, structures, electronics, and control benefit from sophisticated sensors. Flight simulators, flight control systems, navigation systems, landing gear mechanisms, traveler or driver comfort aids, and the like use sensor and sensor systems primarily for monitoring and control. Manufacturing and production engineering is another broad field that uses various technologies of sensors. Factory robots for welding, spray painting, assembly, inspection, etc. Automated guided vehicles, modern computer numeric control tools, machine centers, rapid and virtual prototyping systems, and micromachining systems are examples. Product quality monitoring, machine tool monitoring, and high precision motion control are particularly important in this application, which require advanced sensors and sensor systems too. In medical and healthcare applications, sensor technologies for sensor technology for plant sensor technology for not for plant for patient examination, surgery, rehabilitation, drug dispensing, and general patient care are being developed, and in that context, novel sensors and sensor systems are applied for patient transit devices, various diagnostic probes and scanners, beds, exercise machines, prosthetic and orthotic devices, psychotherapy, and telemedicine. In a modern office environment, automated cleaning systems, multifunctional copying machines, copying, scanning, printing, electronic transmission, and others, food dispenser, multimedia presentation, and meeting rooms, and certainly climate control systems incorporate advanced technologies of sensors and sensor systems. In household applications, home security systems, robotic caregivers and helpers, robotic vacuum cleaners, washers, dryers, dishwashers, garage door opener, and entertainment centers all use a variety of sensors and associated technology. The digital computers and related digital devices use MEMS's embedded and integrated sensors. The impact goes further because digital devices are integrated into a vast variety of other devices and applications. In civil engineering applications, trams, excavators, and other construction machinery, buildings, reservoirs, and bridges will incorporate adopting proper sensors and sensor systems. In space applications, mobile robots such as NASA's Mars Exploration Rover, space station robots, and space vehicles depend on sensing for their proper operation and control. Identification, analysis, selection, machining, and interfacing of components, component sizing, and tuning of the integrated system, like adjusting parameters to obtain the required response from the system, are essential tasks in the instrumentation and design of an engineering system. The rest of our module addresses their issues in the context of sensors and sensor systems, starting from basics and systemically leading to advanced concepts and applications. A robust area in the development of intelligent robots that can mimic characteristics of nature of intelligent concepts. The main goal is to develop robotic sensors that can play the role of human sensory activities for 5 senses. So, sight or visual, second, hearing, auditory, third, touch, tactile, 4, smell, olfactory, and 5, taste or flavor. Sensors in the first 3 categories are in a more advanced stage of development, starting with basic sensors like cameras, microphones, and tactile sensors. The last 2 categories of sensors primarily are used chemical processes and are less common. In addition to these 5 senses, humans also have other types of sensory features. In particular, the sense of balance, pressure, temperature, pain, and motion. In fact, some of the sensory capabilities will involve the use of one or more of the basic 5 senses simultaneously through the central nervous system. In their development, robotic and other engineering systems have long relied on and are inspired by the sensing process of humans and other animals. The basic biological sensing process is shown in this figure. A stimulus, like a light for vision, thoughts, sound waves, and hearing, is received at the receptor, where the dendrites of the neurons convert by energy at the receptor, where the dendrites of the neurons is converts of the stimulus into electromechanical impulses in the dendrites of the neuron. The axons of the neurons then conduct the corresponding action potentials into the central nervous system for the brain. These potentials are then interpreted by the brain to create the corresponding sensory reception. An engineering sensory process, such as that used in a robot, basically uses similar processes. As we will see in the succeeding chapters or parts of our lectures, they involve sensor and transducer, transmission and signal conversion and processing. Generally, if we're speaking about the mechatronic engineering, the subject of mechatronics concerns the synergistic application of mechanics, electronics, control, and computer engineering in the development of electromechanical products and systems, through an integrated design approach. Mechatronics is particularly applicable in mixed domain or multi-domain systems, which incorporate several physical domains, such as electrical, mechanical, fluid, and thermal in an integrated manner. For example, an ABC of an automobile may involve mechanics, electronics, hydraulics, and heat transfer, and may be designed in an optimal manner as a mechatronic product. Mechatronic products and systems include modern automobiles and aircraft, smart household applications, appliances, medical robots, space vehicles, and office automation devices. A typical mechatronic system consists of a mechanical skeleton, actuators, sensors, controllers, signal conditioning and modification device, computer, digital hardware and software, interface devices, and power sources. Different types of sensing and information acquisition and transfer are involved among all these various types of components. For example, a servo motor, which is a motor with the capability of sensory feedback for accurate generation of complex motions, consists of mechanical, electrical, and electronic components. Its main mechanical components are the rotor, stator, bearing, mechanics of the speed sensor, such as an optical encoder and motor housing. The electrical components include the circuitry for the field, winding, and rotor winding, not in the case of permanent magnet rotor, and circuitry for power transmission and communication if needed. Electronic components include those needed for sensing, like optical encoder for displacement and speed sensing or tachometer for speed sensing. The overall design of a servo motor can be improved by taking a mechatronic approach, where all components and functions are treated concurrently in an integrated manner in its design. Study of mechatronics. Engineering should include all stages of modeling, design, development, integration, instrumentation, control testing, operation, and maintenance of mechatronic products and systems. From the viewpoint of instrumentation, which includes sensing, a somewhat optimal and unified approach, not a sequential approach, and has to be taken with regard to component selection, modeling, integration, evaluation, and operation. Specifically, instrumentation has to be treated as an integral aspect of design. This is simply because by design, we develop systems that can carry out required functions while meeting certain performance specifications. Sensor systems and instrumentation play a direct role in achieving the design objectives. Additionally, a sequential approach has been adopted in the design of multi-domain or mixed systems, such as electromechanical systems. For example, first, the mechanical and structural components are designed. Next, electrical and electronic components are selected or developed and interconnected, and subsequently, a computer or a related digital device is selected and interfaced with the system, along with a digital control. The dynamic coupling or interaction between various components of a system dictates, however, that an accurate design of the system should consider the entire system as a whole rather than designing different domains, like the electrical or electronic aspect and the mechanical aspect separately and sequentially. When independently designed components are interconnected, several problems arise. First of all, when two independently designed components are interconnected, the original characteristics and operating conditions of the two components will change due to loading or dynamic interaction. Second, perfect matching of two independently designed and developed components will be practically impossible. As a result, a component can be considerably underutilized or overloaded in the interconnected system. Both conditions being inefficient, possibly hazardous, and undesirable. And third, some of the external variables in the component will become internal and hidden due to interconnection, which can result in potential problems that cannot be explicitly monitored through sensing and cannot be directly controlled. Do you agree with me? Okay, nice. The need for an integrated and concurrent design for multi-domain like electromechanical systems can be identified as a primary justification for the use of mechatronic approach. In particular, when incorporating instrumentation in the design process, such a unified and integrated approach is desirable with regard to the sensor, other components, and interface hardware. For example, consider the design and development of a sensor jacket for a telemedicine system. Recent advances in sensor technologies that are applicable in human health monitoring, such as biomechanical nanosensors, piezoelectric sensors, force and motion sensors, and optical or vision sensors for abnormal motion detection of humans, and may be incorporated into the jacket. However, for optimal performance, the selection, location, mounting, and integrations of the sensors should not be treated independently of the development of other aspects of a jacket. For example, a mechatronic device quotient may be employed to represent the goodness of the overall design of the jacket, where a design index is defined with respect to each design requirement, like size, structure, components, force, accuracy, speed. Then parameters such as sensor size, interface hardware, power requirements, and component location and configuration may be incorporated into the design, which will improve or optimize the process of signal acquisition and processing, body compatibility, weight, robustness, and cost, and also will improve the speed, accuracy, and reliability of the information provided by the sensor jacket. Even though, in theory, the mechatronic approach is the best, or sometimes so often to say optimal, particularly with regard to instrumentation. And it may not be practical to realize the optimal result of instrumentation as dictated by the approach. The mechatronic approach requires the entire system, including the process and instrumentation, to be designed concurrently. This assumes that all aspects and components of the entire system can be modified according to the mechatronic result. However, unless the entire system, including process, is a new design, such as flexibility is often not realistic. For example, typically the process is already available and it is not practical, convenient, or cost-effective to modify some or all of its components. And then, even if the instrumentation is chosen according to a mechatronic procedure, the overall system will not function as optimally as if we had the freedom to modify the entire plant as well. Furthermore, in practice, the available set of components are discrete and limited. Then, even if they optimally dictate a particular set of specifications for the component, we may have to select a component having a different set of specifications. As an example, consider an automated vehicle guide-by system of public transport. Suppose that the system already exists and that it is required to replace some of its cars. Then it is not practical to significantly modify the guideway to accommodate a new design of cars. In fact, the design freedom with regard to the cars and will be limited if it is constrained by a specific guideway design. Even if a car is designed and instrumented optimally, according to mechatronics, the operation of the overall wide vehicle guided system will not be optimal. It is clear that true mechatronic instrumentation may not be perfectly possible for existing cars. And furthermore, since the components for instrumentation, like sensors, actuators, controllers, accessory hardware, may come from different manufacturers, and their availability would be limited, as noted earlier. And it is not practical to realize a true mechatronic product, since the available set of components is limited and may not be truly compatible. Sensor systems are important components in the instrumentation of a control system. The controller, which is an essential part of any control system, makes the plant, like the process that is being controlled, behave in a desired manner according to some specification. The overall system that includes at least the plant and the controller is called the control system. The system can be quite complex and may be subjected to known or unknown excitations, as in the case of an aircraft. Some useful terminology related to control system is listed as follows: plant or process for system to be controlled, input for commands, driving signals, or excitations, known or unknown, output for responses of the system, sensors for devices that measure system variables, like excitations and response, actuators for devices that drive various parts of the system, controller for device that generates the control system signal, control law for relation or scheme according to which the control signal is generated, control system for at least the plant and the controller, and may include sensors, signal conditioning, and other components as well. Feedback control for control signal determined according to the plant response. Open loop control for plant response not used to determine the control action. Feed-forward control for control signal determined according to the plant excitation or a model of the plant. In this figure, we have identified key components of a feedback control system. Several discrete blocks are shown, depending on the various functions that take place in a typical control system. In a practical control system, This type of clear demarcation of components might be difficult. One piece of hardware might perform several functions or more than one distinct unit of equipment might be associated with one function. Embedded systems, in particular, may have distributed multifunctional components where demarcation of the functional blocks will be difficult. Nevertheless, this figure is useful in understanding the architecture of a general feedback control system. In an analog control system, signals are continuous time variables generated by analog hardware. In particular, the controller is an analog device. On the other hand, in a digital control system, the controller is a digital processor, like microcontroller, and hence sampling or encoding of the control signal is not required. The control problems can become challenging due to the such reasons as complex plans, where we have many inputs and many outputs, dynamic coupling, nonlinear, time-varying parameters, etc. And such as a rigorous performance specifications, such as unknown or unmeasurable expectations, such as unknown or unmeasurable responses, where we have unmeasurable state variables and output, measurement error, and noise. Such as unknown dynamics, where we have incompletely knowing plans. Since the operation of a control system is based on a set of performance specifications, it is important to identify key performance characteristics that a good control system should process. In particular, the following performance requirements are important. And first, it's a sufficiently stable response for stability. Specifically, the response of the system to an initial condition excitation that should decay back to the initial steady state in case of asymptotic stability. The response to a bounded input should be bounded in case of a bounded input or bounded output stability. Second, sufficiently fast response for speed of response or bandwidth. The system should react quickly to a control input or excitation. I hope you agree with me, right? Third, low sensitivity to noise, external disturbances, modeling error, and parameter variation, especially as sensitivity and robustness. Fourth, high sensitivity to control input. 5, low error, for example, tracking error and steady state error or accuracy. And 6, reduced coupling among system variables, like cross-sensitivity or dynamic coupling. As you may see listed here, some of these specifications are rather general. And this table summarizes typical performance requirements for a control system. Some requirements might be conflicting. For example, fast response is often achieved by increasing the system gain. And increased gain increases the actuation signal, which has a tendency to destabilize a control system. You should be noting further that what the given here are primarily qualitative descriptions for good performance. In designing a control system, however, these descriptions have to be specified in a quantitative manner. The nature of the used quantitative design specification depends considerably on the particular design technique that is employed. Some of the design specifications are time domain parameters, and the others are frequency domain parameters. As seen before, please, in a feedback control system, the control loop has to be closed, where the system response is sent and employed to generate the control signal. Hence, feedback control is also known as a closed-loop control. Right? If the plant is stable and is completely and accurately known, and if the inputs to the plant can be precisely generated by the controller and applied, then accurate control might be possible even without feedback control. Under these circumstances, a measurement system is not needed, or at least not needed for feedback into the control. And thus, we have an open loop control system. In open loop control, we do not use current information on system response to determine the control signal. In other words, there is no feedback. Even though a sensor is not explicitly needed in an open loop architecture, sensors may be employed within an open loop system to monitor the applied input, the resulting response, and possible disturbance in the significance and importance of sensor and sensor systems remains regardless of the specific control system architecture that is implemented in a given application. We now outline several architectures of control system implementations while indicating the presence of sensors in them. Even in a feedback control system, there may be inputs that are not sensed and used in feedback control. Some of these inputs might be important variables for the plant, but more commonly, they are undesirable inputs, such as external disturbances, which are unwanted yet unavoidable. Generally, the performance of a control system can be improved by measuring unknown inputs and somehow using the information to generate control signals. In feed-forward control, unknown inputs are measured, and that information, along with desired input, is used to generate control signals that can reduce error due to these unknown inputs or variations in them. The reason for calling this method feed-forward control system from the fact that the associated measurement and control both take place in the forward part of the control system. But no, in some types of feed-forward control, the input signal is generated by using a model of the plant and may not involve sensing. In a practical example, consider the nature of gas home heating system shown in this slide. A simplified block diagram of the system is shown in this figure. In conventional feedback control, the room temperature is measured and its deviation from the desired temperature, as we may say sometimes, that point is used to adjust the nature of gas flow into the tunnel. On or off control, though, a thermostat is typically used in such applications. Even if proportional or three-mode proportional integral derivative control is employed, it is not easy to steadily maintain the room temperature at the desired value if there are large changes in other or unknown inputs to the system, such as water flow through the furnace, temperature of water entering and furnace, and outdoor temperature too. Better results can be obtained by measuring these disturbance inputs and using that information in generating the control action. This is a feed-forward control. Note that in the absence of feed-forward control, any changes in the inputs, like W1, W2, and W3, certainly would be detected only through the effect of the feedback signal, like room temperature, and hence the subsequent corrective action can considerably lag behind the cause. No, maybe changes in one of W, and this delay will lead to large errors and possible instability problems. With feed-forward control, information on the disturbance input from W1, 2, or 3 will be available to the controller immediately, and its effect on the system response can be anticipated, thereby speeding up the control action and also improving the response accuracy. Faster action and improved accuracy are two very desirable effects of feed-forward control. In digital control, a digital computer or microcontroller serves as a control. Virtually any control law may be programmed into the control computer. Control computers have to be fast and dedicated machines for real-time operation, where processing has to be synchronized with plant operation and actuation requirements. This requires a real-time operating system. Apart from these requirements, control computers are basically not different from general-purpose digital computers. They consist of a processor to perform computation and to oversee data transfer, memory of the storage of programs, and data during processing, mass storage devices to store information that is not immediately needed, and input or output devices to read in and send out information, like for interfacing with other components and the control system. Digital control systems might use digital instrumentation and additional processor for actuating, signal conditioning, or measuring functions. For example, a stepper motor, which responds with incremental motion steps when driven by pulse signals, can be considered as a digital actuator. It usually contains digital logic circuitry in the motor drive system. Similarly, a two-position solenoid is a digital or binary actuator. Digital flow control may be accomplished during a digital control valve. A typical digital valve consists of a bank of orifices, each size in proportion to a place value of a binary put. Each orifice is actuated by a separated rapid-acting on-off solenoid. In this manner, many combinations of discrete flow values can be obtained. Direct digital measurements or displacement and velocities can be made using shaft and cord. These are digital transducers that generate code output, like in binary or grayscale representation, or pulse signals that can be coded using counting circuitry. Such outputs can be read by a digital controller with relative ease. Frequency counters also generate digital signals that can be fed directly into a digital controller. When measured signals are in the analog form, an analog front end is necessary to interface the transducer and the digital control. Input-output interface cards that can take both analog and digital signals are available with digital control. Uh-huh. Analog measurements and reference signals have to be sampled and encoded before digital processing within the controller. Digital processing can be effectively used for signal conditioning as well. Alternatively, a digital signal processing chip can function as a digital control. However, analog signals have to be preconditioned by using analog circuitry before digitizing in order to eliminate or minimize problems due to aliasing distortion. Like high-frequency components above half the sampling frequency appearing as low-frequency components. And leakage, it means error due to the signal truncation, as well as improve the signal level and filter out extraneous noise. The drive system of a plant typically takes in analog signal. Often, the digital output from the controller has to be converted into analog form for this reason. Both analog to digital conversion, ADC, and digital to analog conversion, DAC, can be interpreted as signal conditioning or modification procedures. If more than one output signal is measured, each signal will have to be conditioned and processed separately. Ideally, this will require separate conditioning and processing hardware for each signal channel. A less expensive but slower alternative would be to timeshare this expensive equipment by using a multiplayer. This device will pick one channel of data from a bank of data channels in a sequential manner and connect it to a common input device. The current practice of using dedicated microcontroller-based and often decentralized, like distributed digital control systems, as industrial applications can be rationalized in terms of the major advantages of digital control. The following are some of the important considerations. First, digital control is less susceptible to noise or parameter variations in instrumentation because data can be represented, generated, transmitted, and processed as binary blocks with bits processing to identifiable states. Second, very high accuracy and speed are possible through digital processing. Hardware implementation is usually faster than software implementation. Third, digital control systems can handle repetitive tasks extremely well through programming. Four, complex control laws and signal conditioning algorithms that might be impractical to implement using analog devices can be programmed. Five, high reliability in operation can be achieved by minimizing analog hardware components. And though decentralization using dedicated microcontrollers for various control tasks. Six, large amounts of data can be stored using compact, high-density data storage methods. Seven, data can be stored or maintained for very long periods of time without drift and without getting affected by adverse environmental conditions. Eight, fast data transmission is possible over long distances without introducing excessive dynamic delay and attenuation, as in analog. 9. Digital control has easy and fast data retrieval compatibility. 10. Digital processing uses low power and low operational voltages, usually up to 12 volts for DC. And finally, 11. Digital control is cost effective. There are many control systems and industrial tasks that involve the execution of a sequence of steps depending on the state of some element in the system and on some external input state. A programmable logic controller, or PLC, is essentially a digital computer-like system that properly sequences a complex task, consisting of many discrete operations and involving several devices that need to be carried out in a practical way. The process operation might consist of a set of two states, means on or off actions, which the PLC can sequence in the proper order and at a correct time. PLCs are typically used in factories and process plants to connect input devices such as switches to output devices such as valves at high speed at appropriate times in a task, as covered by program or ladder logic. Examples of such tasks include sequencing the production line operations, starting a complex process plant, and activating the local controllers in a distributed control environment. In the early days of industrial control solenoid-operated electromechanical relays, mechanical timers and drum controllers were used to sequence such operations. Today, PLCs are run computers. An advantage of using a PLC is that the devices in a plant can be permanently wired, and the plant operation can be modified or restricted by software means or by properly programming the PLC without requiring hardware modification and reconnection. Internally, a PLC platform basic computer functions such as logic, sequencing, timing, and counting. It can carry out simpler computations and control tasks such as PID control. Such control operations are called continuous state control, where process variables are continuously monitored and made to stay very close to desired value. There is another important class of control, known as discrete state control or discrete event control, where the control objective is for the process to follow a required sequence of states or steps. In each state, however, some form a continuous state control might be operated, but it is not quite relevant to the task of the discrete state control. PLCs are particularly intended for accomplishing discrete state control tasks. And the example for PLC applications, consider an operation of turbine blade manufacture. The discrete steps in this operation might be the following. First, move the cylindrical steel billets into furnace. Second, heat and billet. Third, when a billet is properly heated, move it to the forging machine and fixture. Four, forge the billet into shape. 5, perform surface finishing operations to get the required air foil shape. 6, when the furnace finish is satisfactory, machine the blades through. Note that the entire task involves a sequence of events where each event depends on the completion of the previous one. In addition, it may be necessary for each event to start and end at specified time intervals. Such time sequences would be important for coordinating the current operation with other activities and because for proper execution for each operating step. For example, activities of the parts handling robot have now had to be coordinated without the schedule of the forging machine and milling machine. Furthermore, the billets will have to be heated for a specified time, and machining operation cannot be rushed without compromising the product quality, to failure rate, safety, and so forth. The task of each step is to discrete sequence might be carried out under continuous state control. For example, the milling machine would operate using several direct digital control loops, say PID control loop, but discrete state control is not concerned with this except for the starting point and at the end point of each task. A schematic representation of a PLC is shown in this figure. A PLC operates according to some logic sequence programmed into it. Connected to a PLC are a set of input devices like push buttons, limit switches, and analog sensors such as RTD temperature sensor, diagram type pressure sensor, piezoelectric accelerometers, and strain gauge load sensor, and a set of output devices like actuators such as DC motor, solenoid, and hydraulic pump, warning signals indicator such as light, alphanumeric LED display, and bells, valves, and continuous control elements such as PID control. Each device is assumed to be a two-state device, taking the logical value 0 or 1. Now, depending on the condition of each input device and according to the programmed logic, the PLC will activate the proper state, like on or off, for each output device. And hence, the PLC performs a switching function. Unlike the older generation of sequencing controllers, in the case of a PLC, the logic that determines the state of each output device is processed using software and not hardware elements such as hardware relay. Hardware switching takes place at the output port. However, for tuning means on or off, the output devices controlled by the PLC. As noted before, a PLC is a digital computer that is dedicated to perform discrete state control tasks. A typical PLC consists of a microprocessor, RAM and ROM memory units, and interface hardware, all interconnected through a suitable bus structure. In addition, there will be a keyboard, a display screen, and other common peripherals. A basic PLC system can be explained by adding expansion modules, memory, I/O modules, etc. into the system rack. A PLC can be programmed using a keyboard or touch screen. An already developed program could be transferred into the PLC memory from another computer or a peripheral mass storage medium, such as hard disk. The primary function of PLC is to switch, generally saying energize or de-energize. The output device is connected to it in a proper sequence depending on the states of the input device and according to the logic dictated by the program. Consider the schematic representation of a PLC that is shown in this figure Note the sensors and actuators in the PLC. Okay. In addition to tuning on and off the discrete output components in a correct sequence at proper time, a PLC can perform other useful operations. In particular, it can perform simple arithmetic operations such as addition, subtraction, multiplication, and division on output device. On input device. It is also capable of performing counting and timing operations, usually as part of its normal functional requirements. Conversion between binary and binary coded decimal might be required for displaying digits on an LED panel and for interfacing the PLC with other digital hardware. For example, a PLC can be programmed to make a temperature measurement and the load measurement display them on an LED panel, make some computations on these input values, and provide a warning signal or output depending on the result. The capabilities of a PLC can be determined by such parameters as the number of input devices, usually divided by 16, and the number of output devices, like 12. And that it can handle the number of program steps, like 2000, and speed at which a program can be executed. How many steps per second, for example. Other factors, such as the size and nature of memory and nature of timers and counters in the PLC, signal voltage level, and choices for outputs and all important factors. Next lecture, we will be continuing study sensor system in engineering. And now, I hope you enjoyed this lecture, and I am looking forward to see you next time. Bye.